Really nice to be here and get to know people and hang out with old friends. So I want to tell you a little story about degeneracy loci in combinatorics and geometry. And I figured I'm going to tell this mostly aiming towards combinatorics, but I'm going to start with geometry. And as any of you who've seen me talk before, which includes maybe half the audience at least, I'll probably end up talking, well, I will end up talking about Schubert polynomials, and I'll be telling the story of Schubert polynomials from a heavily biased perspective. So before I get into this, let me just say that if I left out your favorite formula for Schubert polynomial, if I didn't write down your best friend's name, feel free to shout it out, and I will happily acknowledge that those people also did wonderful things. I just can't say everything in the I'm supposed to click. Got it. Okay. So let's get started. So I'm going to start a long time ago. I guess you could go thousands of years ago, but I'm thinking a couple hundred years ago, with the following setup. So we have a family of triangles in the plane. Okay, and here they are. We've got 3 points and they form a triangle. And I'm thinking of them as being parameterized, and it could be a multi-parameter family, not just one time direction, but several time directions. And so I'm thinking of them being parameterized by 3 points, just moving according to some polynomial equations in the plane. So there's 3 points, P prime and P double prime, given by pairs of polynomials. And a question that would have made sense to Euclid is the following. So for which values of the time parameters, sort of dimensional time, do the triangles that we're parameterizing degenerate? So you can kind of imagine, and I want to point out, I'm not just asking for all 3 points to be collinear, I am asking for that, but also with a fixed origin. You can kind of imagine like a radar sweep. You're sitting there at the origin. Those triangles are, I don't know, ships out there in the ocean, and you're sweeping around. And when is it that you actually, you only see one ship when actually there's 3? So for what parameters of the time does that happen? So this is going to describe some, well, it's going to be given by some equations on the t's. And you could ask for a finer information, which is like when there's finitely many such parameters t, how many parameters do we have? That's a question that was considered a lot in the 19th century. So, of course, when you write things, when you're asking about collinearity, you're really asking about linear dependence among the vectors that we're talking about here. So an equivalent formulation of this problem is to find the degree, and I'll say what that means in just a moment, of the locus where this matrix, whose columns are the positions of our points, where does that matrix drop rank? Right? So if this has rank 1, that means all 3 of these points are collinear with the origin as well. Okay, the degree in this sense means, well, there's a bunch of time parameters. If I chop those down by linear equations, eventually I'll get finitely many. How many? Okay, so colloquially, that's what I mean by the degree. Precisely, this is going to be some projective variety, and there's a notion of degree of projective varieties, and that's what I'm asking for here. Okay, so as I sort of just mentioned, we know that this is going to be given by 3 equations, 1, 2, 3, saying the 2x2 determinants vanish, because that's how you tell when things are collinear. So although this is given by 3 equations, you can figure out with just by playing around with it a little bit, that in fact, these 3 equations describe something of codimension 2 among all such matrices. And this is sort of the first problem in excess intersection theory. So people noticed this in the 19th century, that you needed 3 equations to describe this locus, but you've only cut down the dimensionality by 2. And right, so I guess I'll talk about that a little bit more. So for example, if we assume that so all of these are linear polynomials, so I could think of them as just coordinates, then each one of these equations has degree 2. And as I said before, if you thought about, well, okay, let's just try to cut down by two equations, because I know it should have codimension 2. Well, if I do that naively, and you can think a little bit about what would happen. Well, this is an equation of degree 2. This is another equation of degree 2. If I have two equations of degree 2, I expect 4 points. But these three equations are not independent, and the 4 points are not actually all on this locus. In fact, the degree of this locus is 3. And I'm giving a little bit of a preview of a way that you can write 3 as a determinant. So everything here is linear. That's why every number here is 1. But if I take 1 plus 1 in the diagonal entries of a determinant, and I take 1 times 1 in the upper right, I'm seeing 4 minus 1 equals 3. So that's just a little preview of the kind of calculations that get done in this field. Okay. So this specific calculation with almost exactly this notation appears in a paper in 1849 by Arthur Cayley, and it's actually it's like a 5-page paper, and it's wonderful to read. And here's where he's doing kind of exactly what I just described to you. So let me go back one more time. Now that you've kind of seen this picture, you see what's going on, right? Why you need all 3 determinants here. If I say this vector is in the same direction as this vector, that's the first equation. And I say it's in the same direction as the third vector, that's this equation. Well, that means they're all collinear, right? Unless this vector is 0. Then these two vanish identically, and then you still need to impose this one. And precisely that is what he is saying in this paragraph right here. And he's telling you how to subtract that contribution to get that 4 minus 1 equals 3. So he goes on in this paper, and he has a little acknowledgement of Salmon as well, because they were talking to each other about this problem. And he goes on to give a more general formula, which looks like this. So you take a matrix which is almost square. It's got one more column than row, so P by P plus 1. And I'm filling it with polynomials, and the polynomials have these degrees. Okay, so you could ask, why have I set this up so that the degrees are kind of set up this way? Well, this guarantees that every minor in the matrix is a homogeneous function of a determinate degree as well. So that's kind of what you need in order to have that. So that's their setup. Look at a matrix that looks like that. And then they looked at this locus where it has where the matrix given has non-maximal rank. And they give a formula, Cayley and Salmon do, as well as others around that time, which says the following: take this series in x's and y's, expand it in u, and take the degree 2 term of u. And so that's something I'll call C2, and I'll use that later. Here's what it looks like. So you take all the degree 2 monomials in X, that's the complete homogeneous symmetric function. You take the mixed terms of linear times linear, and you take the elementary symmetric function in the Y's, so the square for your monomials in the Y's. And that's a formula for the degree of this locus. For example, if we had the case that we looked at before with a 2 by 3 matrix, so P is 2, then there's the formula. And you see that if I had made all the entries linear, so for example, by taking all the y's to be 0 and the x's to be 1, then I get 1, 2, 3. And you see the same thing. I've done it in any other way that you could make all the entries linear.
So that's not your determinant because that had a sign of it.
That's right. This is a slightly different formula, but it's equivalent to the determinant. Yeah. Oh, there's Jake outside. Hey. This is the Cayley Salmon form. So I'm gonna jump ahead a little bit. So jumping ahead half a century or so, Giambelli is okay. Back up. When I've got a p by p plus 1 matrix, you should ask yourself why, right? And part of the answer was because they could, I think. But you want to do an m by n matrix in general and ask for any rank condition. And that's what Giambelli did. So his formula is for the locus of an m by n matrix of polynomials. And you want that matrix to have rank at most r, where now those are as general as they could be meaningful.
In this case, t is just a single number, right? So this degree is actually just counting the number of points.
T is still a multi-parameter. Yeah, I'm eliding that.
But how can they have more than one parameter? I thought it was, oh, those things are polynomials anyway.
Polynomials, they're multivariate polynomials.
Oh,
Yeah. So T, yeah, let me make that clear. T is just a multivariate, is a multi-index. So T0, T1, all the way up to T n for some. So in general, this will have a high codimension. So if we just took one parameter, it would be empty.
So in the previous case, so the other formula, when you set the 3, you set xi's to be 1 and the y's to be 0, or
That would work.
or what?
Or you could set the xi's to be 0 and the y's to be 1, 1, 2, 3. That works too. Or you could set x1 to be, there's other possibilities and they would all give 3. Right. And so the degree of this equation as a polynomial is 2, and that's related to the fact that this has codimension 2. So you need at least 2 t parameters to even see such a thing. Right. Remember this like in the 2x3 case, we had, well, 3 equations, but only 2 of them were really independent. And so that's a codimension 2 situation. So you need at least 2 parameters in all of this. Right. So here's Giambelli's formula. So he's looking at the kind of most general setup. Well, we're going to get more general still, but the one that immediately comes to mind from the Cayley Salmon setup. So we've got m by n matrices, rank at most r. And he says that the degree of that locus is given by this determinant. So what I do is I take some functions that I'm calling C. They will depend on the degrees of the zij's, just like before. They're basically the same kinds of things as before. I'll write them down in a second. You stick them into a matrix where you write Cn minus r down the diagonal, and then you make the index increase by 1 across rows. In formulas, that's this. So I've got Cn minus r going down the diagonal and increasing across rows. And then I take an m by r minus m by r matrix. It's determined. Okay, so here the C is given by, well, the coefficients, just like before, we find them by expanding this ratio, where the x's and the y's are the degrees of the z's just as before. Right, so the degree of zi is xi plus, the degree of zij is xi plus yj, just like before. So whatever, each one of these, each term, each ck here is some combination of complete and elementary symmetric polynomials. It's like the one that we saw before. Now I'm going to jump into the modern era. So in 1974, there was this landmark paper by Kempf and Laxov. And so I'm going to use more modern language. And instead of talking about just matrices, I'll talk about vector bundles on some variety X. But locally, it's just matrices again. I'll say that again in a moment. But their setup is the following. We've got some flag of vector bundles. Every time I write a subscript, that's the rank of the vector bundle involved. So this is something whose fibers are dimension 1, fibers are dimension 2, fibers are dimension n, fibers are dimension n. So that's what I've got on some projective variety X. And I've got a partition, which is just a non-increasing sequence of integers, of non-negative integers. The R here is the difference between N and M, and so I probably want N to be more than M for anything and for the setup to make sense. So, and then like we usually do, like most of us in this room know how to do, we'll write partitions as Young diagrams just by stacking up boxes, 4, 3, and 1 in this case. Okay, so the locus to consider is something like this.
No, so
Oh, yeah. How many degrees do I need to shift it to go to Russia? Yeah, yeah. Forgot which room I was in. I should. All right, so here's the locus they're considering. This number is always impossible for me to remember, which means that probably most of, if any of you knows a trick for remembering it better than the one I know, let me know. But the important thing is I'm going to take some part of this flag, I'm going to map it over to F, and I'm going to demand that, that the rank of that map drop. And I'm going to do that for all pieces of the flag.
So X here is an element of E.
X is a point in the variety down there.
Oh, and I have a fixed. The map from EN to FM is fixed from the beginning.
Yeah, I fixed this map, and then I'm going to look at a map, the induced map, by composing through there. Compose through there. And now I'm calling it X instead of T because I'm looking at points in this variety, but in fact X and T are morphous. So that's the locus. And I sort of gestured at before, locally, this map is given by a matrix, just an M by N matrix. And the ranks of the matrices in question are just the kind of left submatrices. And so what we're looking at is placing rank conditions on the first so many columns. So whatever this is, n plus I minus lambda I, that many columns, and I want the rank to drop by on those columns.
Lambda is an integer partition of whatever number?
It's an integer partition of whatever sum of all the lambda i's is. But so we don't, so in this picture, we don't start with what it's a partition of so much, but the sum of the boxes, the size of the partition actually is important. It tells us the codimension. And I'll put that on the next slide. So the codimension of this locus is supposed to be whatever lambdas are prediction of.
And can you remind F what it is?
All of these are vector bundles, but if you prefer the language of vector spaces, they're just vector spaces that are moving in some family. So in this picture, F is just an m-dimensional vector space because I've got an m by n matrix, and E is a n-dimensional vector space. So locally, that's all it is. So here is their okay. Move away the punchline. Sorry, guys. So here's the setup, and here's their theorem. So their theorem is a formula for the degree. And it is something that looks an awful lot like Giambelli's formula. Except now I'm writing lambdas down the diagonal, and then I'm making it increase by 1 as I go along the rows. And there's this kind of change by row. So I haven't told you what the C of i's are. So as I go along rows, the entries, these kind of series that are telling me which combinations of elementary and symmetric polynomials I should take, those are changing. And essentially, this is the same thing as putting a flagging condition on the Schur polynomial. If you know the Jacobi-Trudy formula for Schur polynomials, this is the Jacobi-Trudy formula for flagged Schur polynomials. And it showed up in this 1974 paper. There's an asterisk here, and this is actually a major contribution of the paper. If you think about what I've said so far, none of it actually makes sense. I was talking about matrices of polynomials and talking about the degrees of the loci they defined. And I didn't say anything about what the entries had to be. For example, if all of those polynomials were 0, then the rank of that matrix is 0. And there's nothing to talk about, right? It's the whole space. The determinant conditions do nothing. So of course, Cayley and Salmon and everyone else knew about all of that. And their answer would be like, well, it's when the entries are generic. But in some sense, it wasn't until this paper that people said what generic means. So generic means that the codimension of this, which you can measure somehow, is what it's supposed to be. And that's the size of the partition. So, and precisely whenever that's true, this degree, that's a precise condition for this, and a precise and checkable condition for this degree formula. So that was Kempfer Maxwell. And now I'm going to jump again to the 80s and 90s and kind of start aligning things together. Right. So before with Kempfer Maxwell, we were looking at flagging one of the vector bundles and mapping to a single one. But once you have that idea, well, why not have a flag of some bundles and then a flag of quotient bundles, and then talk about conditions between all principal n squared of these. So on the combinatorial side of what I'm about to say, this is something that Lascaux and Schutzenberger and McDonald, well, they invented the answer, what will turn out to be the answer, and kind of McDonald cleaned up their story and packaged it very beautifully, and you can read about it in one of my favorite Lascaux publications. And on the geometric side, Fulton realized that you could connect all of the ancient geometry I've talked about to the combinatorics that these other guys figured out. So the input is this setup, some subspaces, some quotient spaces, or subbundles and quotient bundles, along with a permutation, which I'll always write in one line notation. And then you look at the locus where of points where the rank from the pth piece of the subflag to the qth piece of the quotient flag is at most some number. And that number is the rank of the upper left p by q submatrix of the permutation matrix for W. So if in the kind of picture that I had before, I write this vector bundle map as a matrix, I'm just placing rank conditions on northwest submatrices. Yep.
I'll just ask a question kind of about conventions. Let's say that I just pick for each P and Q what a number for that to put as the rank condition. Is that equivalent to some choice of W?
That's a good question. No. So if you just randomly drop down ranks, you can pretty quickly figure out that you cannot, that won't be consistent with a W in general. So there's a feasibility condition, right? So first of all, if I put a rank, so I've got an n squared many ranks, right? But if I'm jumping by dimension 1 in the source space, I'd better jump by at most dimension 1 in the rank. So the ranks can kind of, they have to increase by 1 at most in each adjacent step in order for things to be feasible. So that's kind of the most obvious condition. It's not the only condition. If you just do that, this is a little curious. What you end up with is alternating sign matrices. So there's this other funny condition that that cuts out the permutations. Yeah, so which kind of ranks you can pop down there is an interesting question. Okay, so the theorem, and this is a theorem that appears in Fulton's paper. And so in this language, it's certainly due to him. If you take out one of these variables, I think it's fair to say it would have been known to Lascaux and Schutzenberger about a decade earlier. But the theory is that the answer to this question of degrees of loci cut out by minors of matrices is the double Schubert polynomial.
Where did the, maybe you want to just skip over this detail, but is X and Y related to like the joint roots of the vector bundles?
Oh, I did skip over that detail, didn't I? Yeah, so I should have, so xi is C1 of 6 minus C1. Yj is the Chern class of kernel from Fj surjecting data. In the local translation, it ends up being the same as the degree of the homogeneous polynomials I talked about before. Okay, I haven't told you what the Schubert polynomial is, and I'm not going to tell you what it is in the usual way. So those of you who know the story already know, I'm going to give you a formula for it. But yeah, I'm going to kind of assert by history that these are interesting things to talk about, and that finding new formulas is an interesting thing to do. There's a very incredibly rich combinatorics around these polynomials. And so I want to tell you some of the news story about combinatorics. And the news story of this combinatorics involves gadgets like the one I'm pointing at here, and that I'm going to talk about for the rest of the hour, called bumpless pipe dreams. So let me describe these things to you. I've written a permutation, and I'm not going to write numbers 1, 2, 3, 4, 5, 6, 7 along the bottom, but those are always there on the bottom. So this is 1. And what you do is you follow, you should match things up. So these are wires or pipes that connect like numbers to like numbers. So 1 ends up there. 2 ends up there. 3 ends up at the top. 4, 5, 6, and 7. So that's how you do this. This is a particular choice of doing it, and you might recognize the Rotha diagram, which goes back even farther than I started the story in this picture. So you draw these pipes, and then you kind of put orange boxes in the squares that you missed. So this is something that Lamley and Shimizono introduced under this name in 2018. They called them bumpless pipe dreams, and I'll tell you why they're called that in a second. And Anna Weigand almost immediately, upon hearing about them, realized they were connected to a formula of Lascaux from at least a couple decades earlier, involving alternating sign matrices. And she gave, so if you want to read about these things, you should read her paper. Yeah, it's in JCTA. And so many people since that time have discovered wonderful things about them. There's some more about them later. Why are they called bumpless pipe dreams? Well, I'm thinking of an n squared grid here, and I'm going to tile it with one of these 6 shapes. And actually, that was already a first hint. If you see 6 types of tiles, you should probably realize that it's square ice or alternating sign matrices. And so I think she knew that. So you can have an empty tile, you can have horizontal pipes, vertical ones, crossing pipes. You can have one of these elbow tiles, which didn't happen to show up in this picture. I'll show you some pictures of that later. Or you can have this kind of other way elbow tile. But you cannot let 2 pipes bump together in one tile. So that's why it's called a bumpless pipe dream. And they're thinking of these things as pipes following language that Knudsen and Miller introduced around 2000, which goes back to another formula by Bergeron and Billy from the 90s. So this is a really different formula from that formula from the 90s that I just alluded to. But the name kind of emphasizes that by saying we're not allowed to see these kind of tiles. So how do you do it? Well, to each such diagram, you associate a weight. And I'm going to label the rows by X variables and the columns by Y variables. And then for each box, I'm going to record an Xi plus Yj. We're looking at the Ij box. So this diagram gets that weight. And I've tried, the only meaning of the positions there is to try to roughly reflect where they showed up in this diagram. So that's how it goes. And then the formula that was written down by Lamley Shimizono, and they Anna Weigand's proof, is that the Schubert polynomial, the double Schubert polynomial, is a sum over all bumpless pipe dreams for your given permutation of the corresponding weight. So again, you can imagine different ways to connect these pipes with these labels to the bottom ones, which were labeled 1 through n. And those different, if you just sum up over all those different ways, you get the Schubert polynomial. So that's their formula.
All of them, all of the different bumpless pipe dream for given W has the same number of empty box.
Yes, length many empty boxes. Like the W many empty boxes.
Sorry, but W is not the ordering 3, 4, 2, 7, 6, 1, 5 there, is it?
Well, this is the pre-image.
I mean, that's not, there's more than one column of numbers associated to W.
Oh, I'm thinking of W as a permutation.
Yeah.
So just the W of 1 is 3. W of
Okay,
2
yeah, no,
is 4.
that's what I was wondering, but then how do you get a sum? Because that's giving you a unique pipe dream.
Ah, okay, I've only showed you one pipe dream, but there are many of them. I'll show you a couple more.
For fixed 3, 4, 2, 7.
Yeah, many of them in general. I'll show you.
You didn't use that other elbow. You can.
Yeah, I didn't.
Oh, because you didn't use
this
the elbow.
elbow.
That's why.
That's right. If I just do these, there is in fact only one.
Okay,
But you see, like I could do this guy and go through there.
okay.
So, yeah. Yeah, no, that's a good point. So in fact, not using this elbow is equivalent to having the Rotha pipe dream. So this is actually. Right. The paper, the Lamley-Shimizono paper is called back stable Schubert calculus. And what they were thinking about is, bumpless pipe dream's not in the title. What they're thinking about is, well, you could look at W 3, 4, 2, 7, 6, 1, 5, and Lascu and Schutzenberger and kind of the literature that came out of that emphasize the fact that if I think of 3, 4, 2, 7, 6, 1, 5, 8, 9, 10, etc., it doesn't matter whether you add on Wn equals n for big N. The interesting thing that these guys looked at in 2018 was, well, what about Wn for big negative N? So you could do this too. W0 equals 0, W negative 1 equals negative 1, and so on. And you can try to stabilize in that backwards direction. And if you do that, well, now you can start to see that there are many other ways that this diagram can mutate into others. And I like to think of them as letting these orange boxes drift. Let the boxes drift northwest. And what you end up with is a supersymmetric function in both the x and y variables. This is actually one of the standard ways to write down Schur functions, maybe in code. But let me show you what it looks like. So the first way that this box might drift is if you let this box in the corner move one step to the northwest. And then you can keep going. Once I've done that, I could move any of the other boxes in any of these 3 ways. But that goes on forever, as you can kind of see. What you end up with, like I said, is some sort of symmetric function in all of the non-positive variables. Let me clarify that a little bit. The sum of all of the weights of these things is not itself a symmetric function, but it breaks up into pieces which are. So if you just collect the parts that are symmetric in the negative and x and y variables, that is something that you can do. Okay, and so what Lamley and Shimizono did was say, well, we had a formula for Schubert polynomials. Let's apply that same formula to this situation, letting everything go backwards, and call that the back-stable Schubert polynomial. So in fact, as they wrote it, this is a series and in all the non-positive variables, it'll go on forever. So for sort of other reasons, Bill Fulton and I were thinking about related things. And we were interested we eventually realized we needed to understand their formula. And we wanted to write down polynomials, so finite polynomials, not series. And the idea is sort of simple. It's to actually just collect those supersymmetric parts and put them into new variables, which I will continue calling C's because they're going to look like C's. You end up with something that is almost the same thing as the back-stable Schubert polynomials. We call them enriched Schubert polynomials, and I'll write them with a bold S to slightly distinguish them. So they depend on an auxiliary set of variables called C. These are independent variables. So these things live in a polynomial ring where I've got C1, C2, C3, all the way to infinity. I've got integer many X's and integer many Y's. So the X's and Y's, you expect as I'm going forwards and backwards, I can index them by any increase. So they live here, and in fact, if you do this right, they form a basis for this polynomial ring. They specialize to the backstable ones when you specialize the C's to the coefficients of this series, just like we were doing before. So these are collecting all of the non-positive X and Y variables into a supersymmetric. So this is sort of, I should point out that specialization is faithful. So it really this sort of is a shift in perspective rather than a logical augmentation. One interesting thing that happens is if you kill the X and Y variables, which you can now do, all of the X and Y variables, you get the Stanley symmetric function. When you think about the C's as, say, the complete homogeneuses in the X's.
So, one question, in your XY in this polynomial ring is X0, X1, X2 are the positives.
It's X negative, whatever, X dot, X negative 1, X0, X1, X2, dot. So it's all, yeah, there's integer many of these, and there's integer many of these, and there's natural numbers. And what I'll do with my remaining time is give you some formulas for these in terms of diagrams like the ones we looked at. Okay, so in order to do that, I need to write down a new basis for the polynomial ring. Again, for every partition, I'm going to talk about what's called an enriched dominant Schubert polynomial. So I'll call this S lambda, and it's going to be, this is like a Giambelli-like determinant. So it's like the Kempf-Laxov determinant. Notice the same kind of, I've written lambda I down the diagonal, and I increase by 1 along rows. And this superscript is really going to be some flagging along the rows. So it's the same kind of thing that we saw with the Kempf-Laxov. So here's what this is for any P and Q. I'm going to change my C's by some amount where I'll allow more Y's and fewer X's, something like that. But the important thing to take away from this is that this is essentially a flagged Schur plot. If you set the C's to 0, what pops out of it is just the product over all cells of my lambda of the weight of that cell. And so, and this is the formula for the Schubert polynomial of a dominant permutation. Let me show you just a simple example of that. So here's a dominant permutation. That's the same thing as 1, 3, 2 avoiding. But the way I like to think of it is if you write the Rotha diagram of it, so this is that, then you just get a partition shape sitting in the north, kind of in the positive quadrant. Yep, so there it is, 4, 3, 1. And you could then write down the Schubert polynomial as just a product over these boxes. So like x1 plus y1, x1 plus y2, etc. The crucial fact about these things is that they form a basis for all polynomials as a module over polynomials in X and Y. So just a quick check that this makes sense. I'm thinking of the C's as elementary or complete homogeneous equivalently symmetric functions. So if I just look at the C's, Schur polynomials form a basis for polynomials in the C's. Those are indexed by lambdas. And so then if I add X's and Y's, I get the right kind of cardinality. And then it's just a check that I got the right thing. I have to check that they're independent. That's not a basis. And so, so we have this basis of enriched dominant polynomials, and we've got this enriched Schubert polynomial, and we'd like to give a formula for it. Well, we're going to expand it in this basis. Now we need to give a formula for these coefficients. So for each lambda and each w, I want to know what that polynomial in X1. Okay. And so I'll tell you the formula. Here's the formula. It's gonna be, so without this asterisk and without this condition, it looks an awful lot like the Lamb-Leach-Shimazona formula for the Schubert polynomial. I'm summing over all bumpless pipe dreams for W, some kind of weight. So the key, of course, is that lambda has to enter the picture. So here's the one that we were looking at before. And the lambda of the partition of the pipe dream is just everything that is contiguously in the northwest corner. And here it's the partition 2, 2, 1, 1, 1. And so it's that. That's the lambda. And then the weight is, it's a very simple thing. The weight is just, so the weight of the whole thing is this, which I had on the screen before. The weight star is just everything that's not in lambda. That's all. So you just sum up all of these to fix your lambda, find all your pipe dreams that have this shape up here, and then count the rest of the boxes. It has the right degree at least, and it turns out it's the right degree. That is a formula for these back-stable Schubert polynomials. So remember, each one of these has a nice concise determinant, and then each one of these looks like this. Okay, so that's sort of the result I wanted to tell you about in detail today. I'll just kind of close by mentioning some other things that we've been doing, and some other things that other people are doing, and what else one could do. Yeah.
Maybe I should ask about this.
Yeah.
What's the relation between this and the geometry? I mean,
Yeah, so that's a good question. So short answer is we don't know really good relations. So of course, this gives formulas for the kinds of geometric questions I was asking. That's one relation.
but first of all, this backstable ones is just without the formula even.
Okay, yeah. So what do backstable ones have to do with geometry? So there's a couple answers. So one answer is, so let me look now. We look at a big vector space V. And let me look at two subbundles. So I'm going to go from, I had a subbundles and quotient bundles before. Now I'm going to have just two subbundles. And we can go use dualities to go between those two pictures. And I'm going to look at flags like this, where I've got integer many pieces over here. And I'm going to do the same thing over here, because I'm going to index things the opposite way. And I can look at conditions. So I was looking at kernels before, but now I'm going to look at dimensions of intersections. Again, this is equivalent by K is supposed to be equal to some function that depends on, this is just some function that depends on W. And then this thing will define some locus that is backstable in the right way. So there's some geometric locus that I don't know which, yeah. So this geometric locus kind of sits inside an infinite dimensional Grassmannian, which I'm going to think of as a union over all M of half-dimensional Grassmannians. Something like that. So this is a vague answer to the question, Joel, but like there's a place where this geometry, where the backstable polynomials naturally come up, and it has to do with the geometry of this infinite dimensional Grassmannian half-dimensional spaces.
So in this setup, the E's and F's they're codimension one, each one inside the next.
Each one inside the next, yeah, the way I've set it up, it's a saturated flag.
The reason why in this case you're having two chains of subspaces instead of subspaces and projections?
The only reason is that on my feet, I could write down, well, there's no reason at all, because I didn't really write down a precise formula in a way that you could understand, but it's equivalent to projections. This is sort of easier to.
I think I missed the very, very start of it, but in this picture, these vector bundles is V like is V an infinite dimension.
Let's say V is some infinite dimensional, let's say V is an infinite dimensional space. So V is maybe kind of C infinity with maybe negative let's say C has a basis consisting of vectors indexed by the integers. It also comes with a splitting into the subspace indexed by non-positive integers and positive integers. And then I could look at like a Grassmannian of all subspaces of that, but I have to tell you what kind of subspaces of that. And I want to tell you, they're the ones that came from half-dimensional spaces as I drew this out in both directions. In this setup, and then you can do the same thing with the flag variety. When you do this with the flag variety, these backstable Schubert polynomials are the basis of the cohomology ring of that flag variety. That comes from the geometry. So they're motivated in that sense as well. I'll just wrap up with a few looks around and looks to the future. So in addition to this formula that I just showed you, we have some tableau formulas for Schubert polynomials that come from breaking these things up into pieces and then realizing each piece as something that in fact can be written as a generating function over lattice points in a certain polytope, which is what some tableau formulas at least are. So there's tableau formulas for these Schubert polynomials. They can also be, at least some of them can be written as determinants on their own. And so those are things that I've been working on with Bill Fulton. There's a really interesting connection with alternating sign matrices. The diagrams I've shown you are in bijection with alternating sign matrices. That's one thing. But there's another thing which is related to Jake's question, which is that the degeneracy loci imposing these rank conditions, in fact, it's natural to talk about take an alternating sign matrix rather than a permutation and impose the degeneracy loci conditions coming from that. And that's something that Anna Weigand and Tricia Klein and others have been working on lately too. So they've been looking at the commutative algebra that comes out of those kinds of ideals generated by minors of alternating sign matrices. You can prove Monk and Pieri rules for multiplying. I didn't talk about multiplying these Schubert polynomials, but it's a very interesting thing to do. And Daoji Wang and Pasha Pirlavsky have used these bumpless pipe dreams to do that. There are generalized Edelman-Green formulas for expanding specializations of Schubert polynomials in Schur polynomials. And so Zach Kamaker and Qiangyi Yu have been working on that. And there are some connections to plane partitions. And so Alejandro has been asking me questions about that and telling me things about that. And so I've been learning, and I think we have some answers, but that's a good question. Again, when you see alternating sign matrices and tableaus, maybe that's not so surprising. But okay, so there's lots more going on. So that's what I know is going on now. And let me tell you about some other directions that I didn't talk about much. So one of them is everything I've talked about here is sort of formulas for degrees, which can be translated into formulas for cohomology classes. So there's Chern classes. But there's other cohomology theories, and one of the favorite ones to look at after ordinary cohomology is K theory. And so this somehow measures the finer geometry of the varieties that we're looking at. And it's maybe an interesting coincidence that actually long before Lescaut was involved in the Schubert polynomials, he was involved in formulas for the K theory classes of these things. So this was his thesis, I believe. And much more recently, Anders Spook and Alan Knudsen have been thinking about that. And those are actually sources for all the things I've talked about. So you can look for determinantal formulas for the K theory classes. And I could have told this whole story about that. And there's some remarkably recent work on that. I was involved in some of it. Basically just generalizing Giambelli's determinant to the K theory setting. I think if you want just a direct generalization, that's happened in the last 10 years. So there's applications to the geometry of divisors and algebraic curves. And so Melody Chen and Nathan Pfluger, and I, along with Linda Chen and Nicola Traska, as well as Minyoung Jian, did this, and so I'm mentioning this because this is actually Ken von Laxov's original motivation in writing down the determinantal formula. That wrote down the next paper right after their paper in ACTA in 1974 gives a new proof of the Brill-Noether theorem, which is related to this using Schubert calculus. And there's all of this kind of wonderful combinatorics that I talked about for these Schubert polynomials generalizes to the K-theory setting where the objects involved are called Grothendieck polynomials. And I think Anna Weigand was the first one to write it down. And then Lamley Shimizono have a follow-up paper where they extend what she did. So those are things you could do in K-theory. Another thing you could do is look at other Lie types. So rather than looking at rank conditions on matrices, you could look at rank conditions on symmetric or skew-symmetric matrices. And this turns out to be connected to the other classical groups. The formulas are different. You end up having Pfaffian formulas. So this was, I think, first realized by Piotr Pragach in the 80s. And kind of fleshed out by Billy and Heyman, Kazarian, and then Bill and I looked at that. There's sort of a missing combinatorics here. So the BPD formulas, these diagrams, I don't think we've got good ones for the other Lie types. At least we haven't settled on them. We're maybe in the position that we were in the 90s with Schubert polynomials and other types before Billy and Heyman came along. So they're candidates, but we don't know them. So this seems to be fertile ground. Although these folks have some suggestions. I mean, Kirillov, more recently, Kirillov and Neruse and Evgeny Smirnov, some others. And then maybe a very big question is, what could you do in affine types? So what would a affine degeneracy locus look like? This is going to have something to do with the geometry of vector bundles on P1 in moduli. And Hannah Larson and Isabel Vogt have some answers in that direction. Quite remarkably, by thinking about the geometry of vector bundles on P1, they rediscovered K-Schur functions and the affine symmetric group. So this is, the last 5 years. So there's lots more to do here too. And so that's just affine type A, do affine other types too. And I think that's not.
Any questions? Yes, yeah.
Maybe one, it's something I'm not sure I've understand, maybe it's my English, sorry. You said that the polynomial that arise from the sum of all these pipe dreams when you do the weight is not symmetric, but it breaks into symmetric parts.
I was not terribly clear about that. That wasn't your English, that was mine. So, oh, here we go. Yeah, so let's see. Let me just give you an example. It's not going to be the best example, but it'll do. So let's look at actually let me do this. So here is here's where 0 is going to be, and I'll do like 1, 2, 3, 1, 2, 3, and let me draw this. Okay, so here's W is just the permutation T1, the first transposition, right? And if I can find a so I got a little orange box right there. And so if I don't look at 0 and everything negative, the Schubert polynomial is just x1 plus y1. But now if I start looking at the negative stuff, well, I can start drifting that guy. And without erasing, I'll start drawing the drifts. So I get x1 plus y1, but I should also get x0 plus y0 plus, so it's -1 plus y -1 plus etc. And so so what I was saying is that this stuff out there is that part is going to be supersymmetric. So I'm going to collect all of that into C1. And so then the Schubert polynomial for this is C1 plus X1 plus Y. And then you can figure out what it would be for any transposition. These are extremely simple cases. You get the idea. Does that,
Yeah. Is the orange part is gonna be symmetric.
this orange part is symmetric. Now, like I said,
Maybe not.
this part happens to be
Yeah,
symmetric too,
now
but
it is, but
the rest
not
of
all the time.
the non-symmetric stuff is gonna kind of happen here, and everything back there will eventually be symmetric.
But what do you mean by supersymmetric?
Supersymmetric means that if I take x1, etc., y1, etc., and I evaluate x1 equal minus y1, then it doesn't depend on x1 and y1, they drop out of the formula. So yeah, then the result doesn't depend on x1 or y1. And so if you see, you'll see what I mean if I write this yi. Oh, and it's symmetric in each individually. So it's symmetric in the x's, it's symmetric in the y's. And if I evaluate one of the x's and one of the negative y's. So if I look at the formula, if I evaluate x1 equals minus y1, then that factor cancels and it doesn't depend. Those variables drop out of.
You have a nice scalar product on these.
Question, sir.
The question is, do I have a nice scalar product? And I'm hesitating. Let me answer this indirectly. So for the like finite dimensional ones, the scalar product comes at least indirectly from Poincare duality in the Grassmannian. Now I've gone to this infinite dimensional Grassmannian, so there's no Poincare duality. For ordinary symmetric functions, forgetting about x's and y's, it's related to the Hopf algebra structure on this Grassmannian effect. So there is, so that scalar product exists here if you kill the x's and the y's. If you just include the y's, that scalar product shows up, but now it's kind of bilinear with the y's as coefficients. This polynomial ring is not a Hopf algebra, but it's a Hopf module over the one with just c's and y's. So that's as much as I can say.
Okay, thank Dave again.